Yeah, thank you for inviting me. So yes, I am definitely more on the application side, and so you'll see that throughout the talk. And yeah, so supercomputing and computational physics has been a big part of the culture that we have at Lawrence Livermore National Laboratory. We were founded in 1952, and scientific computing was actually part of that initial portfolio. So it's been a part of our work since the very beginning. And I like this quote because I think it says a lot about the work that we do and the importance of computer simulations in the work that we do. So it is now accepted that in addition to the experimental and theoretical branches of physics, there's a third, computer simulation. And this was a postdoc who worked with Bernie Alder in the late 60s, who is the father of molecular dynamics. So I think that just says a lot about the work that we do, the importance of computer simulation, and how we really do rely on simulations and supercomputing through the work that we do. And you see this in the fact that LLNL and the DOE complex, the Department of Energy complex as a whole, continues to be at the top of the top 500 lists. And so here I'm showing Sierra, which has peak usage of 125 petaflops. And obviously, Summit is also on that list, but I'm from Livermore, so that's the one I'm using. So data science is increasingly becoming a part of this landscape too. And so we are looking into data science and how to incorporate it into the work that we've done for a very long time and move us forward. And so we see data science as potentially spanning this entire ecosystem that we have. And so we have this, what we think of as the design workflows. And so this is our end users who are designing experiments, who are doing a lot of simulations in advance of the experiments. They do the experiments, and then they come back to those simulations to see what they can learn about the experiment through further simulations and what they can learn about their simulations and how to improve those going forward. We also have what I consider to be enhanced modeling. And so the end users are using the codes as a whole. And we're looking at machine learning techniques, AI techniques, on that outside of the loop kind of workflow. But then we're also looking within our physics codes, and that's most of the work that I'll be talking about today falls into this category. We also look at improved system performance, and so this is using AI and machine learning to monitor our systems and make sure that they are working at the right level that they should be working at, and be able to predict when something is not going to go well. And so we see this as spanning this entire area that is so important to us at Lawrence Livermore. We also, underpinning these, we see the importance of physics-constrained predictions, interpretable predictions, and then community engagement. And so we recognize that we are not going to drive in all areas of AI and machine learning. Instead, we want to be able to partner with people. And one of the pieces of this is partnering with academia, partnering with students. And so because of this, we do have several student programs that fall into these categories. A lot of the people a lot of the students that we hire in my area work for the high energy density physics internship, and that spans a lot of the simulation space, but we also have an HPC Academy where people are building clusters like we just heard about. We also have our Data Science Institute student program where the students have a 50% real world project, and then they have more training where they're using more community-driven data sets to learn more about data science in general. So this is a really important thing to us, and we want to make sure that we are continuing to work with the broader community, including students, including academia, but also industry partners. So we've done a lot of research in this area already of how we can be using machine learning in the workflows and within the physics codes themselves. And so here are just a few high-level examples, and I'll go into a few of these in more detail. But we are interested in things like how do we improve those workflows? How do we take some of the effort that our users have to do to piece together a lot of different pieces of their work and make that streamlined so that we can be smarter about how we do that. Then there are things like being able to understand our material interface reconstruction, and I'll go into more details on that. Material discovery, if we look at grain structures, what can we understand about materials and how they'll perform? Looking at turbulence modeling and actually trying to improve the accuracy of our turbulence modeling without increasing the computational cost. Looking at surrogate models and also multi-scale coupling. So before I get too far into this, I want to give a little bit of terminology of some of the things that I'll be talking about during this talk. First of all, we have our geometry that's discretized using a mesh or a grid. And so this is an important concept in a lot of the work that we do. So spatially, we're discretizing in a mesh or grid, and you could see on the left side of the screen a couple of examples of this. And we also discretize time into time steps. And so we move forward in time in these discrete time steps. Then we have fields such as density, velocity, or temperatures that are calculated on the mesh points, so the intersections of those edges there, or on the zones themselves, depending on the field. We have Eulerian simulations where the mesh is static, usually just a Cartesian grid, and then the materials move through it. And then we also have Lagrangian simulations. And so the mesh moves with the materials. So the mesh is not static, it's moving as the materials are moving. And that's what you see on the top left of the screen is this 3D Lagrangian simulation where we have this can and the mesh is on the boundary of the can, and then as the can is being crushed, the mesh has to move with it. But what we do a lot at Lawrence Livermore in my area is what's called arbitrary Lagrangian-Eulerian simulations. And so this is a hybrid between these two, between the Eulerian and the Lagrangian simulations. And you see that down on the bottom left of the screen. So the mesh moves, but it doesn't have to move with the materials. And the reason that we do this is because we have areas where we can't allow it to move with the materials because there is high vorticity. And I'll talk about that on the next slide. So on the left side, you'll see a movie, and it's a very simple simulation, but it's a shock tube. And so we have two different materials, and we have a shock wave coming in from the top. So now what you're seeing is pressure, and that shock just hit the second material, the bottom material. It started at the top, and it moved down, and that shock is moving down to the bottom, and it will bounce off of that. And what you see happens here is that the materials move so much that if the mesh was forced to follow it, it would become tangled. And so you can see this in these blow-ups in the middle of the screen where you see what the mesh looks like, and then you see how the materials are deformed so much that the mesh can't follow it anymore. And so we are using the ALE, arbitrary Lagrangian-Eulerian technique, to make sure that we could continue to run our simulations even when we have these high areas of vorticity. And what you see here is, this idea that if you don't allow the mesh to relax away from the materials, they could tangle, they could become inverted, and then you have non-physical behavior. And so this problem is typically solved with hand-tuned relaxation strategies. And so a user would normally go in and say, I know that it's going to tangle when the pressure gets to this level, or when an angle gets to this size. And because of that, they're creating their own heuristics for solving the problem to allow the simulation to complete. So one of the areas where we've been working significantly over the past several years is trying to train a relaxation strategy that can significantly reduce the user burden. So as the simulation's running, we can get information from each of those zones in the mesh. And what's being shown here are some metrics about the geometry. So the angles, the skew, but then also some physical quantities, so temperature and energy. And then we're labeling it with a notion of how far it is away from getting into a bad state. And so the idea is that if we collect a lot of this information and we train a model to do this, then within a running simulation, we can pass this information into a neural network and do the inference phase. So basically, it looks like a function call where we pass the information in and we give a prediction for how far away from that tangled state we are, so that we can then start to do some relaxation without a user having to go in and having to determine that based on their own heuristics. And so where we are with this now is that this is moving into the user community. So we're building on top of an LDRD, Laboratory Directed Research and Development project, where we have had a lot of students working on this effort. And now we're taking it and we're putting it into our actively running physics codes. So the initial results showed really high accuracy. It was using random forests. And we knew that there were scaling issues with random forests. And so we've been working to improve those models. One of the things that we've done is looking at the imbalance of the training data. If you look at these meshes, the vast majority of the zones are nowhere close to coming into a failure state. It's a few zones that cause simulation to end because they come into a failure state. And so there was a huge imbalance in that training data. So there's a lot of pre-processing that we need to do correct sampling of this data to get out a good balance of data. And we also are looking into generalization into noisy data. And what I mean by that is that it is getting relaxation applied to it because a user is still interfacing with it, and they may want to add their own relaxation strategy in addition to this automatic relaxation strategy. And so coming up with some generalization techniques using convolutional neural networks is helping us address those problems. We're also engaging with the user community to provide more quantitative analysis of the results and trying to assess what is ideal. In this situation of mesh relaxation, if we relax too much, we're losing accuracy. If we're not relaxing enough, then the mesh can get into a tangled state. And so oftentimes the result is over-relaxation to make it work, but that's not the right answer because we do lose accuracy. And so we're looking at evaluating quantities of interest against experimental results. And if we can understand that, we can engage the user community to help us define reward functions so that we can employ things like reinforcement learning. To this point, we've mostly been using supervised learning for this. And we're also using this as a test case for a proxy application using some of the new hardware that we have or that we will be getting. Another example of work that we're doing in this area is looking at material interface reconstruction. And if you go back to that concept of Ale, we have the mesh that does not conform to the geometry. So if we had geometry that looked like this plus sign that you have on the left side of the screen, but then you map it onto a mesh where the mesh does not follow those boundaries, we lose information about where those boundaries were. And so what we really have now is a concept of, in every zone, we know the percentages of the materials, but we don't know where the boundaries are in those materials. And then we try to figure out where those boundaries are during a running simulation. And we try to create these new interfaces where we don't know where they are. So a zone may have, we might know that it's 30% of the green material and 70% of the red material, but reconstructing that can be a difficult problem. And you could see in this picture in the middle that we don't do a perfect job on that, even when we have a high resolution background mesh. And if we go to a low resolution background mesh, we often have no idea where the material is. And so we can end up with these very unphysical clusters of material, and that's not capturing the correct physics. And so the idea here is that if we're training on actual geometry, that we might be able to avoid some of the common problems that we see in heuristic solutions that we currently use. So if you look at these various background meshes, you get different types of patterns as far as how much of the volume fractions are in each of those zones. And so what's being plotted here in the middle row is with that background mesh that looks different in each of those cases, you have a grayscale information about how much of the material is in that zone. And that's really the only truth that we have at this point. And so if for the high resolution, it looks pretty good. You could pretty much tell that it's a plus sign. But then when you get to the low resolution, you can't tell anymore, even though all of these are actually the same shape. And they're also not unique, obviously. And so what we're doing is using a methodology to train a lot of different images. We are creating different images. We're doing a lot of variations on those shapes, and then we're training it with the original shape that we had. And in addition to these types of shapes, we're also doing intersections of the shapes, unions of the shapes, trying to create more complex shapes as we go. And the results that we're seeing here are very promising. So if you had the original geometry, the top picture shows you what those volume fractions look like. So again, this is the only truth that we have. And then the bottom picture shows you volume preserving reconstruction that we would have in some of our codes. And then you can see if you use that as an image, and then you're mapping it to you're training it, giving it the label of the initial geometry, you could get pretty good predictions of what that geometry should look like. And what we see, though, is that we get sometimes too good of predictions. And so this is the same type of situation, but we have a much more complicated shape here. And you can see what the volume fractions look like, and you can see what a reconstruction algorithm would give you. And then what we see is what our neural network gave us. And as you can tell, these are very good. Almost, well, I will say they're too good. There is no reason that we should be able to capture some of this detail without it being overfitted. So we recognize that this is an issue, and so we're trying to add to the diversity of the training. We're also noticing that the current algorithm does not preserve the volume fractions that it was given. That is the one truth that we have, and so we need to make sure that we're able to preserve it. But in this example, you can see that, that the original shape that we have is much larger. The area is much larger than the reconstruction that we have. And that is violating the rules that we have. And so we're working to incorporate changes to that. So some of the next steps that we have in this area is looking at these volume fractions and making sure that this is becoming part of our loss or reward function explicitly, and that we can enforce that. We were originally looking at modifying some of the thresholds to start adding more volume into the image so that we were post-processing this way. But what we ended up with was something that was very noisy and somewhat akin to the original problem that we were dealing with, where we were seeing this, this discontiguous material. And so we're working on making that better. We're also incorporating active learning techniques to handle some of the new types of geometries. So instead of overfitting and then trying to extend it to something new and not being able to do that very well, we want to be able to recognize that the model is changing as it sees more materials. We're also looking at how this algorithm will work in situ. And this is a theme that you'll see throughout a lot of this talk, is that our end goal is to be able to put these into our running physics calculations, where we're running on CPUs and potentially GPUs, but we are also trying to do this machine learning in the same application. And then finally, looking at multiple materials. These are easy examples so far, where we're just looking at the two materials, but once we get to 3 materials, that gets more complicated. Here's another example, and this is just a very short one, but this is looking at creating surrogate models for our modeling. And so in this example, we had hundreds of simulations, full 2D simulations that were used to train a neural network. And then we used that neural network as a surrogate so that we could run very, very fast calculations to get an idea of how the full simulation would run. And so in this case, the inference runs at about 4,000 times the speed of the full simulation. The maximum mean squared error across the cycles is 1.6%. But what we actually see in this third image is that the error is much higher at the boundaries. And so this is not perfect. It's not a perfect representation of the simulation. And the error can be quite high in some of these areas. But since this methodology is used as a filter for our full simulations, and we could run it so fast, it's still a great way to explore our design space before we get into our calculations. We're also looking at machine learning to improve our multi-scale coupling. And so in our physics calculations, we are often running at very different scales, both spatially and in time. And so what we do is we have schemes to handle this. But what we'll normally have is in our continuum model, where we're at the material level, we'll need to get information that's at a different level, maybe an atomistic level. And so we will often do things that increase our memory footprint and make it so that we're losing accuracy in the process. And so here's an example of doing this for opacities. So before running our full simulation code, where we're running at the material level, we'll perform a lot of atomic physics calculations to get information about opacities. So this is for different materials across different density and frequency space. And then we'll create a table from all of that data. Then at runtime, what we do is we read in these huge tables. We'll do a lookup of those tables, and then we'll do a linear interpolation for these. And the interpolations can be more complicated than this, but this is the simple idea here. And so this is really fast, but we are losing accuracy. And because of these large tables, we have a lot of memory because of this. And so what we've been looking at is using a neural network instead to do the interpolation. And so you start out the same with the same type of methodology where we're performing a lot of these atomic physics calculations, but then instead of putting them into just a table, we use those to train a neural network for regression. And then during our continuum code, we are just doing inference on that neural network. And so it's increasing the calculation. I mean, even the inference is a lot faster than this table, or sorry, it is a lot more compute intensive than the table lookup. But with that, we're able to increase the accuracy that we could get and decrease the memory. And so here's an example of some of the results here. And this is using iron and looking across the density and frequency. And then we omitted some of them. We did hold out for cross-validation. And so what we saw is that the neural network has accuracy comparable to the existing tables where we have the slices that we know. When it gets into the interpolation phase, it is more accurate than the interpolation that we were getting with the linear interpolation scheme. And it uses a lot less memory. But unfortunately, what we see is that the highest error is actually where it matters the most for this problem. And you can see that on the left side of the screen, that we have the original and we have the neural network solution. And it looks like they lie pretty close on top of each other. And even looking at the error, it's pretty low, and actually what we would consider to be okay. It falls into a range where we consider it to be okay. But unfortunately, it's the spiky nature of this data that we want it to be most accurate where we have these peaks. And that is where it's the least accurate. And so this is something that has been informative to us, is that although it does very well and our cross-validation score looks really good, when we go and we interact with our physics community, we realize that that's not good enough for all of our problems. And so we're interested in other ways that we could be helping here. And one of the things that we're talking about is using machine learning to predict which tables are needed. And this is not just based on the materials at time zero, but how the materials evolve during the runtime. And that is where we could benefit from having a smarter way to determine which tables are needed. Another application, which is outside of the physics code, so this is more in that workflow kind of idea, is looking at radiographic analysis. So we do a lot of experiments, we do a lot of simulations, but one of the things that we've seen as a bottleneck for some of our experiments is being able to analyze radiography, basically X-ray images that are coming out of our experiments. And so here's an example of our National Ignition Facility. It has this ARC capability. It's advanced radiographic capability, where they use the beams to be able to get an X-ray image of the target inside of this. So this whole realm here, that's the yellow in the middle, it's this cylinder, and it's a gold cylinder, and half of the laser beams come into one of the holes, the hole that you see on the top, and the other half can come in through the bottom. Now this cylinder is about the size of a pencil eraser, like one that's on the top of a pencil. So it's very, very small. And then inside of this, you have a capsule that's about the size of a BB. And so it's very tiny in there. And we want to get information about that capsule and how it is reacting to the laser beams. And so you can see this image off on the right, which is the radiograph coming out of it. But going in and manually finding the features of interest is time consuming. And so we want to increase the efficiency in that. And so what we're looking at is medical imaging for how machine learning is being used for medical imaging and how that is transferable to our needs. And here is an example of using machine learning to recognize brain tumors. And what we've found is that we can apply this type of a model. This is the thing that has become complicated with this, though, is coming up with enough labeled images to be able to train a model like this. Like I said, doing the analysis of a radiograph is painful. It takes a long time, and we don't have a huge number of them, especially that have been labeled and then archived. And so what we're doing now is using our simulations to be able to generate what we call synthetic radiographs. We have a capability for that. But then we also have the 3D geometry of what that image, where that image came from. And we have information about that simulation that we could then use to create a high fidelity label for it. And so we're starting this looking at clean radiographs where we don't have any of the artifacts that you would normally see in an experiment. And what we're seeing with this is that we're able, through cross-validation, which I've already said is not perfect, but through cross-validation, we're seeing very, very good results in being able to find the features that we care about in this. Now that we are at this point, we want to start introducing the distortions that you would see in experimental radiographs. And our radiographic capability allows us to do that. And so if we can create radiographs that look very much like the experimental images, and then we can label them with the ground truth of the simulation, then our hope is that when we introduce it to experimental radiographs, then we can get a pre-labeled image back so that we can find the areas of interest. Now, again, like the ALE application, this will take some effort to get it into a state where we can have confidence in it, and we'll work with our user community to do that. And so our dice coefficient in this is looking very promising, and so we're excited to move forward in this area. We also have a lot of data infrastructure needs, and we did not see tools that were addressing this directly. So data infrastructure is fundamental for our needs for machine learning. And machine learning, especially deep learning, we need a lot of data, we need verified labels, and we need provenance, especially when we're talking about a lot of the work that we're doing where our labels come from simulations. And so we need to know which version of the code it came from, how that code was run exactly, so that we can go back and clean some of that stuff up if we find that we had bugs that would have affected this. And so it's really important for us to know exactly where those simulations came from, exactly where our data came from. And we work in an HPC environment, and our traditional databases just aren't that common in this environment. And so that has been a struggle for us. The typical use cases for tools are not always considered secure or able to run in this HPC environment. And so we have a tool called Kosh. This is Sanskrit for treasury that we've been developing to solve some of these problems. And so it actually it sits on top of databases. We're not trying to redo any of that work, but it's done in a safe way. And so this allows for multimodal data sources that can be searched and accessible by end users that are authenticated. We're incorporating sampling algorithms, so both spatial and temporal, into this so that we can just pull out a subset of the data to use for training. And then our data sets can have multiple files associated with them. We also are looking at data that's distributed across different organizations, different labs, different computer centers, so that we don't have to have it all sitting on one of our our computers at Livermore. And we're also looking at how users can just query to get the information that they want, the training data that they want, and then incorporating in augmentation for that. As you might guess, data augmentation is a very common thing for a lot of uses of machine learning, but the data augmentation techniques that apply to images don't apply to all of our use cases. So here's a little graphic, to kind of show some of the same things that I was just talking about. But you can write different loaders so that any type of data can come into this format. And we store metadata, and we store links or information about where the full simulation data is. And so a user can be sitting out here and query Koch for the metadata and basically browse through the data that's in there, and then use a Python interface to get a lot of data out of it for training, again, using sampling and data augmentation techniques. We're also finally looking into exploration of new machine learning hardware. And so this is something that is pretty new, and we're just engaging in this now, is specialized hardware that's emerging and how to integrate it into the HPC space. Most of the applications that I showed are things that we want to be doing within our physics codes. And so we're not planning to rewrite our physics codes. We want to be using the same hardware that we've used for our physics codes, but explore new hardware for pieces of that. And so right now we're looking at a Cerebras chip. This is not the only thing we're looking at, but this has been announced, and it's being integrated into Lassen. And so Lassen is our smaller version of the Sierra computer. So this is work that's in progress. We're looking at ways that we can test this for different types of applications in the scientific computing programs. So one thing that we are interested in is high precision scientific simulations. And so you could think of this as GPUs, where GPUs were created for graphics, but we're using them for more general purpose needs at this point in time. And so we want to be able to understand, if we have hardware that is specific for machine learning, how we can also use that for other things potentially too, maybe optimization problems, other things that don't completely fit the mold of machine learning, but can be very similar. We're looking at frequent machine learning training. As we know, the training is very expensive, and so we're looking at that that is frequent, but we're looking at very high frequency inference. And so we have this little graphic down below, is that we have our physics simulations, and every time step we might be doing a lot of inference. We don't foresee doing training at every time step, but we might be doing a lot of inference at every time step. And then there's maybe training every, say, 1,000 time steps and inference. And then we're looking outside of that, and so once per simulation, we might be doing training and inference. And then there's also this other part of integrating it into our experimental campaigns. And so looking at experimental data, and we might be doing large ensembles of calculations, and then with that, we take that information and try to compare it to experimental results that we have. And one of the use cases that we're looking at right now is this ALE piece that I talked about at the very beginning of the talk. And that is really where we're looking at potentially very high frequency inference. In this problem, we're talking about inference at every time step for every mesh element. And so that's a lot of data that we have. And so what we're trying to address with this is not the speed of the inference, But if we are using an accelerator to do this, what are the memory and bandwidth issues that we have? And is it worth it? And so we're looking at things like slack time. What is the time that we have between when the feature set is available to when we need the inference completed? And if we can do our shipping of data over to an accelerator, get an answer, and send the answer back to the CPU in time, then we can consider that to be a free calculation. So we're looking at that type of thing for our different hardware. And I just want to note, something about V and V with all of this, because verification and validation comes up a lot when we start talking about machine learning. We see machine learning fail in very bad ways, very, very drastic ways. And we need to address that to really incorporate machine learning into our normal practices. And so a lot of the things that we're doing now are what I would consider to be low-risk applications. Things like ALE, the material interface reconstruction, we already use heuristics to solve these problems, and they're not perfect. We recognize that. We also are doing things like looking at neural networks as surrogate models that can be tested with the full simulation after the fact. And so these are areas where we see low risk, and we see that we could make headway using machine learning to solve these problems in a better way, even if it's not perfect. And we have many research projects at Lawrence Livermore that are looking at physics-informed machine learning, looking at interpretability and being able to interrogate the model, looking at sparse data and transfer learning, where we're taking a model that's been trained on a different domain and then applying it to our domain with a small set of data. And so we're doing a lot of work in those areas. And I do expect that, as research in these areas matures, then our machine learning applications will become higher risk because we'll be able to do that. But short of that, we still need things like reproducibility. We still need some amount of uncertainty analysis. And so we are making it a priority for validation and verification on our training data. Since these models are built based on your training, based on your data, it's important that that information is correct. Is it correctly labeled? Is it correctly representing our real space, our real data space? And then we want to be able to make sure that the models that are being used are correct for the application. We don't want to use techniques that are built for one type of application that don't make any sense on other types of applications. So we need to make sure that we are doing that correctly, and then also recognizing when our predictions are outside of our model scope. And so this is, we've dealt with this problem for a long time. Is we understand that once you get into extrapolation space, that is you can't trust your predictions in that space. We need to apply the same types of concerns to our machine learning applications. So this is an important piece of the work that we're doing, but it is also something that I think we can have a pragmatic approach to. And finally, this is back to the beginning. We're looking across this entire space. I just want to emphasize that community engagement is a really important part of this. This is both for industry, for our hardware vendors, for universities. So moving forward, we recognize that we want to be engaging. And many thanks to lots of people. There's a lot of work that's going on here. And obviously, there are a lot of people that are involved with it. Thank you.
Thank you, Katie. I do have a couple questions that have come in.
Okay.
Let's see. The first one. Instead of using arbitrary Lagrangian-Eulerian, what is the disadvantage of just using Eulerian simulation?
Oh, okay. So when we do use Eulerian simulations, we do not represent the material boundaries as well as we can. And so because we don't know where the material boundaries are, we also don't know where any of the quantities are. And so our physics loses accuracy because of that. An Eulerian simulation with very, very high resolution can capture that a lot better, but then you're paying for it with your memory costs, and you have to increase your parallelism for compute costs, and for both compute and memory costs. And so we have chosen the hybrid to try to accurately represent the boundaries while we're reducing the number of unknowns overall.
Okay, thank you. Another question was, with less statistically significant data, have you thought about using one-shot learning techniques as opposed to synthetic data? I thought it was great that you used the other approach, but was just curious if you thought about using a different approach. I know for MRI, it's a pain for having statistically significant data and face a lot of the same problems, artifacts, et cetera, as you mentioned.
So no, I haven't. And so if somebody wants to share information with me on that and how that could help, I would love to get that kind of information.
Okay, and that was the last question. So again, thank you very much, Katie.
Thank you.